Hello, everyone. This is Spencer Snolling from Hatch, and I'm welcoming you today to the GPSX webinar. We're going to be talking today about modeling membrane bioreactors, MBRs, with GPSX. So I'm glad that you've been able to join us, and I hope you're doing well today. Okay. So my plan for today, as is the usual plan, is I'm going to talk a little bit about membrane bioreactors, a little bit of background information, and then focus most of today on talking about how we can model them with the GPSX unit processes that you can drop on your drawing board that represent different configurations of MBRs. And as you may know, if you've used them in the past, we have a lot of model options available that allow you to adjust the complexity and sophistication of the model. So I'm going to talk about using them in their very simplest sense and also going to model transmembrane pressure and flux through the membrane, which is turning on the most advanced features of the model. So we'll have in a total of 3 desktop demonstrations today, as per usual. I always like to try and run some demonstrations that are interesting and work in a kind of way that is like how you will be using the model. And then I'm going to wind things up with talking about various tips and advice for using the models, for setting them up, and getting the most out of your time with GPSX. And at the end, as always, if you have any questions, please type them into the questions box as we go along at any point, and we'll just let those collect up. And then at the end of the webinar, I'll stick around for a few minutes and answer as many of those questions as I can. Okay. So just a little bit of background on membrane bioreactors. MBRs are a high-intensity activated sludge system that uses filtration in one way or another to concentrate and retain the biomass solids in your bioreactor rather than using secondary clarifiers as you would normally see along with a RAS channel or some pumping to be able to bring back the concentrated sludge. So there are many different types of MBR systems, but some of the most common ones, like the one that we're showing here, that hollow fiber system, are arranged in cassettes, and very often they sit right in the bioreactor itself. And the idea is that you want to basically have them sitting right in the mixed liquor, and then you filter, take a permeate out through the membrane surface, and you hold back all the solids, keep back all the good bugs that you want to keep, and get very low solids in your effluent, basically 0 solids coming out, and then your treated water will move on that way. So one of the major advantages is that you can have a much smaller footprint than a conventional activated sludge. If you have the in-tank kind, basically you don't need any footprint at all. You're going to replace the space that you would normally have for the secondary clarifiers, make that available to do something else. So, so they are also obviously very efficient at doing solid separation. So you're going to get very low, if negligible, solids in your effluent, in your permeate. They do have an extra cost, though, of course, in terms of the energy required to draw the permeate out of the system. And they do have some other operational considerations that you have to take into account. They have to be cleaned and backwashed and keep the solids and, you know, just general maintenance to keep the membrane surface in good shape. There are a number of different technologies out there. 2 of the most common are the flat surface MBRs, where you're drawing the liquid through the surface of the flat surface, and also the hollow fiber MBR. So they're long straws, basically, where you have a circular kind of cylinder of membrane surface, and you're drawing all of the flow up through that surface and up and out the top. Both of these I've seen in situations where these have been in-tank MBR systems. There are many vendors of MBR technologies worldwide. I actually sat down to do a little bit of Google search there so I could get a handle on that. I found over 60, I think, at some point. Most of the major wastewater technology vendors out there have an MBR technology, an MBR product of some kind or another that they have, and they've been widely used both for municipal wastewater treatment and industrial wastewater treatment as well. And I've been fortunate to have the opportunity to model in both of those situations. So when you want to model this type of a system, the idea is you want to be able to capture the activated sludge behavior, but do it in an MBR context where your MBR model is going to hold all of the solids in the same way that the system will work in reality. So you want to be able to have a specific unit process, like this one right here, that is going to be in tank, doing solid separation even before it leaves to go out of the tank. Keep all those solids in there, and then you can configure the rest of your GPSX model around that to be as accurate as you can. So the MBR unit process model is basically a bioreactor model and a solid separation model put together into one object. We have both plug flow and completely mixed versions of the MBR model. We also have an anaerobic version that has a headspace like a digester, and I'm going to come back and talk about that in more detail towards the end of the webinar. All of these are using the regular Mantis 2 biological model, or if you're using one of the other libraries like the greenhouse gas library or the Mantis IW industrial library, you know, all of those kinds of variations, they all have these MBR objects in. So it's a regular biological model. We don't actually make any other changes to the model. It's the same as what you would find in the conventional activated sludge tanks. But it does have a custom aeration model. And now the reason for that is, as we'll see shortly, we do have a second aeration system in there to do coarse bubble aeration over the surface of the membranes to kind of scour off some solids. And so that requires a custom aeration model and actually having essentially two sources of aeration together in the same tank. And so we'll see shortly how you can investigate and play around with that and get some interesting information out of it. And as I mentioned early, you can actually turn on a couple of extra features in these models to get at doing a little bit more sophisticated modeling. And we can have variable flux through the membrane and then calculate what transmembrane pressure would be required to be able to get that flux happening. So you can find all of our MBR units by opening up the suspended growth processes, where you find all of the regular activated sludge processes. And down at the bottom, or towards the bottom there, you'll find the membrane bioreactor. That's the plug flow version on the top there. We can have then the completely mixed version of that. And then, of course, the anaerobic MBR that I mentioned as well earlier. Now, just to be clear, the plug flow MBR is very much like any of our other plug flow objects. It is essentially a number of completely mixed tanks in series. And in this case, the very last one will, by definition, have a completely mixed tank with a membrane in it. So it is essentially the same thing as the situation we have with conventional activated sludge, where we have either CSDRs and you can drop a whole bunch of them on your drawing board and hook them together, or you can combine all of that together into one particular unit. Now, I tend to use the plug flow MBR a little bit more frequently than the other options. Mostly just it's a little tidier on the drawing board there, and also because it does have a few more sort of graphing and output options when you combine all of the reactors together into one object. You can get those really nice colored bar graphs. But to be honest, it works either way, and you're welcome to work with whatever makes you most comfortable. So any internal recycles that you would want to do, like say you wanted to pump from this last zone back to one of the earlier zones, you can do that inside this object just the same way you can for a regular plug flow object. And in fact, I'm going to be showing you an example of an A2O system with that setup, and I've used the plug flow reactor with 3 tanks in series to do that. Okay, so looking at the completely mixed MBR is kind of a good way to get a handle on where everything is in this particular unit, how the connections work. So first of all, of course, just like any one of our other bioreactors, we have input coming in. So this is whatever is your waste stream coming into the system from the upstream object or your influent that's coming in. We have a connection point in the middle of the right-hand side, which is the filtrate. So this is going to be as if it is passed through the membrane and you're taking the permeate or the filtrate out. And that's what is going to be going on downstream. That is your treated flow. The pump connection point is actually a pump of the remaining stuff that's in the bioreactor itself. So it's the regular bulk liquid, the non-filtered part. So this is where you might be recycling something back to an earlier stage of your activated sludge system, or typically where you would waste your sludge in an MBR system like this. So this pump is the unfiltered part. There is actually an overflow connection point, which under almost all circumstances will not have any flow coming out of it. But it is there. It will show that concentrations, just the same as the pump. It'll have the concentrations of the completely mixed tank. Basically, as you'll see later, we're going to have a controller on the filtrate in order to keep the water level such that it never overflows. But I suppose there are some circumstances where it could potentially happen, and in that case, you would see some overflow coming out of your system. Okay, so I wanted to go through so that you can get yourself really familiar with the setups that we have here. Go through the model options page and the input menus that we have. Now, they are fairly lengthy because there's kind of a lot of stuff going on in here. We're kind of combining these two different technologies together. And so what we did was we split the stuff that you've already seen for bioreactors in terms of their physical and operational sets. So that's the physical tank and operational tank settings. And then we made the membranes have their own physical and operational settings as well. So there's a few more menus that you might be used to seeing. So first of all, the thing you need to know is this first menu, model options, is where you can turn on and off some of the more advanced features. They will be off by default. This is where you can switch to having a variable volume tank and where you would turn on the calculation of the flux and transmembrane pressure and the backwashing activity that would be associated with that. The tank volumes, local environment settings, membrane details, resistance of the membrane, and so on, all of that stuff is in the physical menu. The operational menu is for the tank basically the same that you would find at a CSTR, but the operational for the membrane would be where you find the backwashing and so on. And then all the rest of these menus, they're basically the same as what you would find in a CSTR. So there's nothing special about membranes in any of these ones. These are basically your biological model settings, the kinetic growth rates and so on, operating cost and whatnot. Okay, so to go through those first couple of menus, this will allow you to sort of see where the most important things are to keep your eye on. This is what the model options menu looks like, and this is under its default settings. Do not calculate backwash or TMP. If you want to turn that on, you can just flip this menu down and turn it on. That will start so that it does more dynamic activity and we have backwashing happening. And we also calculate that TMP value. And also there's a few other things that are going to sort of go on in the background there as well. The volume calculations, they do allow for volume to be calculated and for volume to vary over time. As you can imagine, if you're having a system where you've got the more advanced model running and you're doing backwashing at a regular rate, there will be a variable volume happening because at the time when you're backwashing, you're not going to be filtering. So there will be some accumulation of flow in that particular system. So it's going to kind of go up and down over time. Okay, so on the tank side, by the tank we mean the reactor part of it, the physical and operational menus are basically the same as what you would find in the equivalent conventional activated sludge object. So for either completely mixed or plug flow. So you set the surface area, you set the volume of the tank and temperature if you're going to do that. Operational, that's where you set your diffused air rate and do I have a DO controller on? Am I doing any internal recycles? All of that stuff basically the same as what you've already used to. However, for the physical membrane settings, this is where we're going to set the details of how much membrane surface area do we have in the tank and what is the properties of that particular membrane. So you'll see here membrane surface area, the solids capture rate, and so on. So by default, we set a solids capture rate of 99.99% of the solids captured on a concentration basis. That is usually exactly what you would have. I know some people even set it just 100% capture. So basically, you're taking the solids and you're saying that is the amount of solids that are going to be retained on the surface of the membrane. Note that we also actually have a capture rate for a couple of the soluble components as well. So what we're saying here is we're actually going to capture colloidal substrate and potentially some soluble inert material, but you'll notice by default it's only at 10%. It's at a much smaller rate than what you would normally have. So This is where you would come in and you could kind of try to calibrate your model for the membrane performance. But usually I don't find that we have to alter these settings, the capture rates, very much. The membrane resistance and membrane fouling settings, we're going to come back to and show in a little bit more detail later. These are the ones that are required for calculating the transmembrane pressure calculation. So these are things that are theoretically a function of the type of membrane that you are using. Now, normally, under the simpler default settings, and where you're using the simplest version of the MBR model, there's really only these three parameters that you need to worry about, and the default settings tend to be fine. But you basically are only going to see those ones active under the default settings. Okay, moving on to the operational settings. Like, first of all, we've now set the details of how much membrane surface area we have and what is the properties of it. Now we're going to say how is this membrane operation going to work. So one set of the top half of the menu is really about the operation, how much flux is being withdrawn, and how frequently are we backwashing. So you'll notice here, if you're going to have the backwashing and TMP calculations turned on, this is some of the information you will have to fill in. What is the frequency of the backwash? How often does it happen? How long does it happen for? And how much flow do we push through in the backwards direction through that membrane surface in order to blow those solids back off into the bulk liquid? So this is showing by default every 15 minutes for 30 seconds, we push 2,000 meters cubed per day backwards through that flow. So during that time, during that 30 seconds, it is not filtering, and that's what's causing overall the volume to go up and down in the tank. There's also the cross-flow air. This is the scouring air, as it's sometimes called. The cross-flow air that's bubbling over the surface of the membranes. It tends to be a coarse bubble aeration that's there to remove solids back off into the liquid as well. But at the same time, we want to capture that oxygen transfer. That can be a key component of what's happening biologically in this system. So there's some aeration settings there as well. And then lastly, you'll find how frequently do we do a full chemical membrane cleaning. And so that means often means taking the membranes out of the tank, or sometimes in-tank cleaning can happen too. But basically, this is something that is going to, in essence, reset the fouling, in this case, every 6 months. Now, as I mentioned before, if you're only using the simplest basic settings, then these are the only three parameters that you'll really have to worry about. Okay, so I want to start with a very simple demonstration of a simple aerobic MBR. We're going to use the completely mixed version here. And just to kind of get you so that you have a bit of a feeling for it, I've set this up as primary effluent, this influent object here. So I did that just so that you know by opening up this menu, and I clicked on this primary button down here. What this does is it fills this column with typical primary effluent concentrations and characterizations, just in case you didn't know that button was there. So that's set up as a default primary effluent. And then we have an aerobic MBR here. And I'm using, for the most part, default settings on all of these things. You may, oops, I meant to show you, I'm also basically running this in the simple mode, right? Do not calculate the backwash or transmembrane pressure, and we're doing the fixed volume. And we have the filtrate here moving off to this overflow section with the famous GPSX happy fish there. Okay, so what I'm going to do is I'm going to run a steady state solution to start. And let's take a look at this aerobic MBR. So we can see that coming in here, the ammonia coming in is 25 and leaving it is 0.37. And, we're getting full nitrification for the most part. And we can see that we're basically doing all the type of removal that we would want to be able to see. So under the wastage that I have specified here, which I believe is the default wasting, that results in a mixed liquor of 3760 milligrams per liter. And we can see in the filtrate, the solids concentration is 0.376. That's that 99.99% removal on a concentration basis. So that's why this number divided by 1,000. So that basically is basically next to zero solids leaving this particular system, and then obviously it's working nicely. So a couple other things that are worth noting. If we slide further down in your quick panel here, you can see some of the details about the aeration system. And this will be a little different in the MBR in the sense that we keep, in terms of the aeration stuff, we keep the biological air and the scouring or cleaning air separate from each other so that you can actually see some of those details. So here we can see the biological airflow is 833 and our cleaning airflow is 417. So basically we're showing that we have, you know, twice as much air being used for biological than we have for the cleaning. And there's our total oxygen transfer as well. So I actually opened up one of the other menus and broke out some other details. Here you can see not only the airflow that we're doing, but also the oxygen transfer rate here as well. So you can see, yeah, most of the air that's being used by the biology and getting in to be that residual and so on is coming from the biological air, and some of it is coming from the cross-flow cleaning aeration that we have. One thing to note is if I go back to this panel here and I slide down a bit, our DO is actually 3.5. So it's a little higher than what you might expect to see because, of course, we've got this excess aeration for the cleaning. And in fact, this is interesting and complex behavior for the DO controller. We may find that in many cases, if we use a DO controller, for the system, and we turn that DO controller on and we give it a DO set point of 2 or 3 or whatever number we like, it may behave a little differently than you expect because it's already got this other secondary aeration source that might be providing some of the effort that it needs to do that. So it's an interesting aspect of how these systems work when you've got this dual aeration system happening in the same tank. Excuse me. Okay, so I think that kind of shows you a little bit of the details. It's a pretty simple, straightforward type of model when you're using it in this kind of simple context without the extra stuff turned on. I've done a lot of modeling. Most of my projects have been set up with using this completely mixed tank and using it in the simplest mode. That's the majority of the work that I've ever done with MBRs for my projects have come using this particular setup. Right, okay, let's go back to the slides. Okay, so now I want to move on to talking about the more advanced stuff. So let's move on, beyond the simplest setup, and now let's turn on those extra features and talk about modeling transmembrane pressure and the flux through the membrane. So what this means is we now add in a whole extra set of calculations and an extra mass balance into our model. In addition to keeping track of what's going on in the bulk liquid here, we are now going to see what happens to the solids that move onto and off of this membrane surface. So as we have filtration happening, you'll see some of the solids will move on to that surface. And we go into backwashing mode, it pushes them back off the surface into the bulk liquid again. And so we actually incorporate in quite some detail a complete mass balance of all of the particulate state variables, the particulate components of this mixed liquor onto and off of. That is happening 100% of the time, along with all of the other stuff, the aeration models, the biological calculations. This backwashing effect is also happening too. In addition to that, as we mentioned before, we have this cross-flow air scouring. So we're bubbling bubbles over the surface of that membrane, and that removes some of the solids. The cross-flow air is actually assumed to be continuing on all the time, even when we're backwashing. And so that air will be there, and it will be removing some of the solids, and you can even calibrate how quickly it removes the solids off of the system, if that is fine. So nonetheless, that is there, and it's doing two things. One of them is removing the solids off of the membrane, and the second one is it's actually providing oxygen that's going to be mass transferred into the liquid and potentially used by the biomass. So when you're using the backwash and TMP options, the model will calculate the flux through the membrane rather than just assuming flow in equals flow out, like it does when you're using the simplest option. The TMP and the flux are a function of the mass of the solids on the filter surface, the membrane itself, and other things going on, like how the system's being operated, including the sludge viscosity, the temperature, membrane fouling. So there's a lot of kind of things going on there. And basically we use this resistance and series model to be able to calculate the TMP from the flux that we know is happening through that membrane surface. So we're going to use this equation. It's got the membrane flux, which is a function of transmembrane pressure divided by the viscosity, and then these three resistance terms. One of them is the membrane resistance itself. Another one is the cake layer resistance, or related to the amount of solids on the surface. And the last one is the fouling resistance. So let's look at these in a little bit more detail. These two things are the ones that we want to be able to relate to each other. So we're going to be actually calculating the transmembrane pressure from the flux. And we do that by having a water level controller. So when you have these advanced features turned on, we will either, if you have it as a fixed volume, we will either assume what the flux is, or if you allow the volume to vary, which is the most complicated version of the model, we will require you to have this water level controller on. And what it does is, it's basically like having a PID control loop on your permeate pump. It essentially keeps the system such that the water level is constant. And that's a fairly realistic way to do it. One of the previous versions of this, very early drafts of this model, we had the controller on the transmembrane pressure itself, but we learned that it's much more realistic to do it on the permeate pump. So we know those two values, we can calculate those, and then we have these other terms. So we can calculate the TMP once we know all of these things. Viscosity is something we calculate all the time anyway, as part of our environment variable set. The membrane resistance is actually something that you will have entered in the menu. So here it is here. Note the very large values by the defaults. It happens to just work out to be a big number based on the units that we work in GPSX. So very large number there. The cake layer resistance is actually a two-step process to figure this out. As I was showing you earlier, excuse me, basically we're going to calculate this resistance as a function of how much solids are on the membrane surface. And so, of course, this goes up and down as backwashing happens. And so essentially what we do is we use a calculation to get from the total mass of the solids that are on the surface to a thickness. So we get a solid's thickness, and then from there we can calculate a resistance. So there's a few parameters involved, and there's a couple of equations to go through. I won't go through them here in detail today, but what I do recommend is taking a look in the GPSX technical reference. I believe it's chapter 6. There's actually several pages that describe all the process we go through to get from solids to cake layer resistance. And then the last one is the fouling resistance. So this is a separate issue from the amount of solids on the surface. This is referring to like the sort of permanent plugging of the holes, or the permanent scaling or precipitation of something in the surfaces of the membranes such that it is going to impede the flow. And we have a calculation here that we've picked up from a paper that describes how this relationship changes over time. Now note that you can adjust the parameters of this relationship here. RF max is the maximum fouling resistance here. And then the fouling rate constant is this K. And T here is the amount of time since the last cleaning event. And so what happens is basically we have this relationship, and every time we do a cleaning event, T goes back to 0, which means this goes back to being 0 resistance, and then it starts to accumulate again over time. And so you can control how bad the fouling gets and how fast it gets there, but it is not a function of anything other than just time. And so I'm going to come back and talk about how you can do some more interesting things than that too. But I want to show you what the effect is of these two issues, the one being the backwashing and the other one being the membrane cleaning. So the backwashing events, you can actually see them if you run at a small enough communication interval and a small enough window that you could see these things happening. So this entire simulation here is actually just a few hours. We can see every 15 minutes there's a spike. And what this is the backwash event happening, blowing all of the solids off of the membrane. And then for a short period of time, it has a really high permeability, and a lot of flow moves through it. Of course, that means it filters a lot of solids back onto the surface again right away, and it gets back down to its sort of operating permeability, or its operating flux. And so, but you can see that actual detail. Now, if this is something that you would like to be able to play around with and adjust over time, you can adjust those parameters in the model. Like what happens if we go less frequently or more frequently? You can see what effect that has on the particular system at hand. Okay, so then I ran another simulation. Both of these, by the way, were with the layout that I just showed you earlier. This is actually 200 days here that I was running. So this is, again, the backwashing was happening all of those 200 days and so on. But I wanted to run a long one so that you could see how the transmembrane pressure increases over time in order to maintain a reasonable flux. And what's happening there is that this is going up over time because that fouling resistance, the third term in that resistance in series model, is increasing over time until we get to our cleaning event. Cleaning event happens, that gets reset, and now we're back down to it, and then it just starts over again. So this is something that you can replicate in your system. And if you were doing an analysis on what's the trade-off between cleaning and energy usage or something like that, then this could be an effect that you could take into account. Okay, so I did want to mention, if you want to go even one more step, even more complex, is that we could take advantage of the GPSX customization features that allow for this resistance in series model to be actually customized. You could actually replace some of these terms with something else that's even more interesting and more advanced than what we already have. We've had people ask about this in the past, and so that's why I'm bringing it up today. For example, that fouling resistance equation here, you could replace this with something that would be, a function of not just time, but maybe time and soluble COD concentration, or maybe some other thing. So it allows you to sort of even do more model development above and beyond what we've already done here. And so if you're interested in doing that, please contact us, and I can show you what you need to do to make this happen. Basically, you will write your own equation and make up your own parameters, and then you can put that into your layout, and then that will calculate rather than using our equation here. Okay. So what I want to do now, to switch back to sort of more process-oriented stuff rather than membrane-oriented stuff, is to do another desktop demonstration. And this one is a little bit inspired by a tech support question that I had actually many years ago, where we had a client who was coming into our office to do training, and they had set up a BioP system with an A2O system, but in an MBR context. And so we were helping them do that as part of our typical training session. And we got into this long discussion about the way that this person had set it up. And he was a little bit confused about why he wasn't really seeing really great MBR, sort of, A2O type BioP removal. The orthophosphorus was being removed, but not as low as he had expected. And then anytime he tried to optimize some other part, like to try and maybe, change up the denitrification a little bit, it seemed to make the BioP worse. So what we did was we played around with his model, and I always remember this was sort of, when I was a bit more at the beginning of my career than where I'm now. So I was learning a lot more, at that time about how to take advantage of what the models can do for you. So this story has always stuck in my head. So I have set up a similar situation to what he had. Now, this is an A2O MBR. This has got 3 reactors in it. If I go to the physical tank menu, you can see 3 reactors, and I've got volumes and everything already set up. And I've also got 2 recycles in here, the ones that you would normally see for an MBR, one from the 3rd reactor to the 2nd reactor, and then another one from the 3rd reactor to the 1st reactor. That would be your RAS recycle that you would normally see in a conventional activated sludge system. You have to do that in an MBR, because if you don't, then all your solids will end up at the end of the MBR, and you'll have no biomass at the front end. So we have to make sure we put that other recycle in there. And so I was discussing what should those recycle ratios be that made up for this interesting question. Excuse me. Okay, so let's run, first of all, steady state simulation here, and we can see what's going on with this A2O system. So if I click on the MBR here, we can see there's our 3 internal reactors here. And we can see the ammonia goes down. We can see the nitrate comes up, but it's, less than 6. So that's actually doing pretty well. And then we can see soluble ortho-P. In fact, it's actually easier to see it on these graphs here. Excuse me. On these graphs here, this is the kind of setup I like to use a lot of the time to sort of troubleshoot BioP and other types of BNR systems, just to sort of get a visual feeling for what's going on. So we can see here oxygen. There's our 3 reactors, lots of oxygen in the end. And these 2 are supposed to be 0 because that's an anaerobic zone. This is an anoxic zone. So our denitrification appears to be working well. We're bringing back this nitrate to here. It's being denitrified. That's great. We're getting the ammonia down here. It's mostly being oxidized away, so that's great. And the BioP is working the way we would expect. We're getting lots of release in the anaerobic zone and lots of uptake in the aerobic zone. So down to 0.14. And so that looks pretty good. So now the issue that this guy wanted to investigate was changing that recycle from the 3rd zone back to the 1st zone. That's this one right here. And what we did was we set him up with a sensitivity analysis. So that's what I want to show you here. This is a nice tool that you can use in GPSX. If you've never used the analyzer before, it's really fun to play with. I apologize, I'm losing my voice a little bit here. Okay, I'm going to set this to a step analyze action. We actually have an entire webinar on our website that talks about how to use the analyzer in GPSX, if you'd like to check that out on our YouTube channel. Okay, so what it's going to do now is I'm going to turn on the analyzer and I'm going to run a steady state solution at each of the steps along the way. So it's going to start at a ratio of 1 and up to 5. 1Q up to 5Q, 1 times the influent flow rate. So what I've plotted here is the effluent orthophosphorus versus that recycle ratio. The RAS ratio here, you can see, of course, it starts with pretty decent performance, but then it immediately goes up and is now more than twice as what it was before. Or by the time we get up to 5, it's actually the effluent orthophosphate is like 1.7. So this was kind of highlighting what was going on in this particular system. He wanted to increase that to sort of balance the mixed liquor a little bit, but then that was costing BioP performance. And what we can do is plot any number of other variables versus that same independent variable. So what we did was we plotted DO and nitrate in the anaerobic zone. So you can see here that by the time we go from 1 to 5, the nitrate is actually doubled. And the DOs come up from basically negligible to, well, maybe not so negligible anymore. I mean, it's not high, but it's also not 0 either. So what we were telling him was, or what we were able to see as a group together playing with this model, was that there was a big impact of recycling from the 3rd, the aerobic zone, all the way back to the anaerobic zone. And essentially, we were killing that anaerobic zone by putting oxygen in it. And the reason was because if we go back and take a look at that BNR profile here, if I look at the DO, so let's look at the DO, it's close to 0, sort of 0, but this is like 6 or 5.7 milligrams per liter. It's a lot more than you would expect, right? So, and in fact, in this case, the DO set point is actually 2, but yet we have like 5.7 milligrams per liter of oxygen. What's going on there? The reason is because the way his example was set up, and also the way I have it set up here, is that we have a lot of cross-flow air, and it's putting a lot of residual oxygen in the aerobic zone, and that's getting dragged back around into the anaerobic zone and making it not so anaerobic anymore. And so what we said was, well, can we cut this number back? So now I'm going to use it really drastically cut back here. And then let's go back to our sensitivity analysis and run it again. And so what you're doing now is we're going to maybe try that recycle ratio and see whether we can get a lot of benefit out there without breaking the whole system. And so now you can see this number here, the soluble orthophosphate in the effluent is now not creeping up the way that it was before, and that is because our nitrate is behaving and also our oxygen is doing better here too. So we're not making our lives difficult by not making our anaerobics not really anaerobic. So that was a really interesting exercise that I remember doing at the time, and I thought that was super fascinating and very MBR specific. And so you can capture it very nicely in our model. Okay, back to the slides. Okay, I want to talk real quickly about the anaerobic MBR. This is the model that's actually the most recent ones. The other two models have been around for a long time in GPSX, probably close to 20 years, I guess. I think it was version 4. But the anaerobic MBR came along somewhat later. It is generally something I find used more in an industrial context. So it's a completely mixed MBR. You'll notice it does not have any bubbles in it because, of course, it's not aerated. So it's anaerobic only, headspace modeling just like a digester. That's why you see that there's a lid on it here and that we have our gas connection point like we do for the digester. The TMP and backwashing is not present in this model. We don't have that other extra set of calculations in here. But what it does include, though, is the heating and biogas energy recovery model that is part of the digester model. So if you were doing this and you were generating gas and you wanted to investigate, okay, what could be a benefit here? What could we capture and get back from that gas production and heat retention? You can those calculations are available to you to use. So just like the digester, if you right-click on the gas connection point at the top of the anaerobic MBR and go to the gas variables menu, you will see a prediction of the gas flow, just like you would in the digester, the total gas, and then the breakdown, so you can see how much CO2 you're getting and how much methane and so on. Okay, so let's take a really quick look at this. How am I doing for time here? I'll just keep it moving along. Back to modeling mode. And today I'm going to use actually one of the examples that are here in the sample layouts menu for the anaerobic MBR. So for those of you who have not investigated this yet, if you go to the file menu, go to sample layouts, there are like 100 different layouts now, I think, or more. Various types here. We have all different kinds of typical plant designs already put together for you. The unit process examples is sort of like all of the specialty items and other new objects. Every time we release a new object, we put a layout here so that you can understand how it works. So here's the anaerobic MBR. So let's open that. And just to show you real quick here, this has got the anaerobic MBR object right here. We're having an influent. Now, one thing that this is very much a industrial application here. You'll see, for example, if we go into the influent characterization, the influent BOD is like 1,500 and the TKN is like 100. So this is a very highly concentrated industrial waste coming in here into the anaerobic MBR and then followed by an aerobic system to polish up and get rid of anything else that's left. All right, so if I run a steady state solution here, you can see right away if I just double click on the anaerobic MBR, bring up the quick panel here, you can see, for example, one of the things right away is that it's a very high mixed liquor concentration. This is 26,000 milligrams per liter, and also you'll notice a SRT of 25 days. So this is an MBR system, but it's really more like a digester almost. And so it's doing that typical type of treatment here. You can see there's VSS destruction. You can see, of course, that we have gas production. If I slide this panel down here, here's our total gas flow rate. We can see very high methane content for the particular influent characterization that we had. And also you'll note here that we're doing the pH calculations are turned on for this the simulation, and we can see that we had to use some alkali dosage here, some base dosage coming in order to keep the pH up high enough, because otherwise, if we hadn't done that, then this would have been down around 6 or so. And so there's an example of where you could sort of play with the different aspects of the model. What's the chemical cost versus what we could potentially recover in terms of cost from generating a bit of energy out of this thing. So nonetheless, there it is. You can open up that sample layouts menu and play around with that model and get some experience with it from there. Okay, so coming to the end here, just a few tips and advice for setting up these MBR models. Most of the time, as I mentioned before, users stick to the simple model option, so no TMP and backwashing and fixed volume. That does the job, I would say, majority of the time. But if you want to get into that level of detail, you want to understand exactly what the performance is going to be like on this particular system, you can turn on those more complex details and dig right in. That's one of the great parts of being able to adjust the complexity of the model. So as I mentioned earlier, there are no specific changes to the biological model parameters. There have been instances I've seen at conferences, people sometimes talk about it, but generally I have not had that experience at all. The default calibration of our Mantis 2 model works really nicely in the MBR context, just as much as it does in the conventional activated sludge. But one thing that is different is that some of the default parameters in the aeration model are different in the MBR than they are for regular tanks. So you'll find that alpha is different and the oxygen transfer is different. And you'll find different values for the regular biological air versus the scouring and cleaning air. So that we took quite a bit of effort to do that. I think we also, the DO controllers tuned a little differently, trying to keep it a little bit, more realistic for the types of technologies that are going to be used in those two particular purposes. Okay, so winding things up here, some final thoughts. The MBR models have been around for a long time. They're very commonly used. I see when we get tech support from people or talk to the users who use our software, a lot of people have used the MBRs over the past 20 years, very well tested and well calibrated over time. There's that different levels of complexity, being able to turn on or off those more complex levels of the model allow you to sort of match the effort level and the amount of data you're going to use and so on to the task at hand. If I just want to do some simple, straightforward design, then you can just pop it down and go with it and you're all set. It's really an excellent tool for comparing, existing treatment designs versus potential upgrades. I see a lot of this actually where somebody will build an existing plant and then in the same layout, just copy that same plant, delete out the conventional activated sludge and put an MBR in. And then you run them together side by side in the same GPSX layout. Then you can plot all the effluent quality and operating cost and everything side by side on in the same graphs. And that works real nice. And we, as a matter of fact, have an example like that in our sample layouts menu. So there are actually several layouts that have MBRs in them in the sample layouts menu. There's a couple that are set for just the regular, just to highlight how the MBRs work, but there's a couple that are kind of like that process comparison as well.